Yeah, thanks a lot for the invitation. It's a pleasure to speak here, my first time. This is part one of a 4-series lecture jointly with Alberto Vizzani, who's over there, on motives. And let me give you the rough plan of the lectures. So today this is part one. This will be about algebraic motives. So this is done by me. Then there is a part two, which is also today, this afternoon, which will be done by Alberto, which is on rigid motives. And there's a part three. That's, so to speak, the sequel of my first lecture on Thursday. It will be on motivic Satake equivalence. And there's a part four done by Alberto. So it will be on p-adic cohomology theories. Okay, so it's easy. It's Tata, the plan. So maybe as a quick word of motivation. So for me, the main motivation to look at this was to have some construction which doesn't depend on the choice of a cohomology theory. In particular, not on the choice of, for example, L when you do L-adic cohomology. And so what I want to do today in this part one are two things. First, I want to start with a recollection on motives, as tailor-made to the application of the geometric Satake. And part two, I would like to discuss this formalism, if you like, in the case of the Hecke stack. Okay, so let me start with one. So this follows the work of Wojewodsky, Ayub, Szysinski, de Glies, and many others. And so what is the basic setup? Let's say we have X is a finite type scheme. Scheme over the integers. We're going to associate to it a category. So my notation for this category will be DMX for derived motives on X. And the following construction. So we look at the category of sheaves, or rather infinity sheaves on smooth schemes over X, equipped with the étale topology. And for simplicity, I choose values, so sheaves of Q vector spaces in the rational numbers. Make some things simpler. Oops, need a bit more space. In that category, we're going to look at the A1 invariant objects. So that's supposed to mean, so
do you consider derived category or just actual shapes or complexes?
Yes,
or shapes with various integers?
That's a great question. So like this written, maybe it's an infinity category of sheaves. But in this case, actually, you can show it's just the derived category of the actual sheaves. these two concepts agree. I mean, or a bit more technically, infinity sheaves here are automatically hypercomplete.
But why you write Q and not DQ? It should be then sheaves is various interactions.
Yes, I should write DQ, that's right. So what does it mean to be a one-invariant? So object here is a contravariant functor on the smooth schemes over X, and we ask this condition here for all objects in our site. Okay, and then, oops, need even a bit more space. And then there's a second step in the construction. You invert the Tate twist. So it's an object. So this category has a tensor structure. It's symmetric monoidal, and you invert this object here. And this is QX twist 1. You take the multiplicative group. It's a sheaf of abelian groups. Then, oops. Well, we work with Q coefficients, so we tensor it up and shift it by -1. There may be different ways to think about this shift, but one way of thinking about it is that, let's say, under the analytic realization, you want that object to go to the Tate twist in analytic homology, and this is where this shifts plays a role, for example. And by construction, this is somehow the universal category satisfying the following list of properties. So tells étale descent. Satisfies A1 invariance.
But this GM is not A1, GM tensor Q is not A1 invariant because peak, so schemes can.
Right, if it's non-reduced, you mean, yeah. But well, maybe you only know it a posteriori. This category only depends on the underlying reduced scheme. But, yeah. Oh, you want me to make it A1 invariant? Yes. Yes, you're right.
I mean, the higher cohomology, which is also, I mean, if X is regular, it's maybe better, but otherwise it's not.
Yeah.
You also have non-semi-normal, which are reduced.
Sorry?
You have non-semi-normal schemes, which are reduced.
Right. Okay. Yeah. So. Well, let me say this. With this, I mean the oh.
You can see the HCP file.
Well, yeah. Okay. Let me leave it like this.
Just make it A1 invariant.
Yeah, make it A1 invariant. Yeah. Okay. So. It's also Q linear, and well, the Tate twist is invertible. I guess these are the striking features, so to say, of this category. And let me start with a list of properties. So first is the six-functor formalism. Namely, this construction upgrades to a functor I would like to call the M upper star from correspondences on finite type schemes over the integers to infinity categories. And this is lax monoidal. And namely, a correspondence, so drawn like this, from x to y. This is mapped to, so there's a pullback functor, and there's also a compactly supported cohomology functor from dm of x to dm of y. And such a functor encodes a couple of data. So maybe first some additional properties. So dm of x, this is by construction stable presentable. And also it has a symmetric monoidal structure, just written as a tensor product, which is induced somehow from the tensor product on sheaves, and then it passes through the localization and through this inversion process. You have also right adjoints to those functors. So G lower star, F upper shriek, and inner homomorphisms. And these are subject to familiar properties you would encounter for other cohomology theories, for analytic cohomology, for example. So that's base change, the projection formula. Actually, those two are part of the data of such a functor. And then there's some additional things. This is localization, excision, or localization or excision, meaning if you have a closed sub and its open complement, you get exact triangles or fiber sequences. And you have also Poincare duality, expressing the upper shriek functor in case of smooth maps as a twist and shift of the upper star functor. Okay. These are pretty nice properties on formal construction. And another thing I also would like to mention, which, as I understand, also comes up again in Alberto's talk, is that dmx, this is in fact compactly generated by the so this basically is the notation for an object in the site, so quasi-compact object, for the motive associated to it. And then I guess I have to add the twists here. Maybe only the negative ones, but yeah. And here this G, maybe I write it here. This is the left adjoint of G upper star in case of smooth map, which somehow comes naturally with the construction. Okay, so here's a quick remark. I'd like to point out, so in fact there exists a variant which is basically given by applying Verdier duality to the whole functor, and I denoted dm upper shriek. It's also a Lax monoidal functor from correspondences to well, let's write like this: compactly generated presentable categories, and it maps a correspondence to, oops, G upper shriek F lower star. Okay, it will be actually this what we will considering for the hacker stack, and the reason for this I explain later. There's a quick part B. There's an analytic realization for, well, if L is invertible on OX. Namely, we have the constructible analytic sheaves on X. And this functor is the unique co-limit preserving functor that on representables, so such that on the generators maps to this, where this is the left adjoint of the star pullback in analytic cohomology. Yeah. Okay. Let me also, so far so good, and somehow what can make this category difficult to work with is actually the computation of homomorphism groups in that category. And
but then it's not X and something else, Z lower star of Q of QU or Q, because
oh yes, thank you. Sorry.
Well, U is smooth over X.
Yeah, I want to do it for those generators here.
Okay, but then you give it on generators, but then you have to extend it to
yes
to morphisms and so on. So
you're right. In fact, there is a much better way of defining this. It's you can define this category with integral coefficients, and then this functor is the L completion functor. But if you do it in presentable compactly generated categories, that's a much better way of saying what this is.
Saying it at this level, couldn't you also just remove the Tate twists and require it to be symmetric monoidal, and then kind of
yes,
kind of by yeah, more or less universal property you get functor.
Right. Okay. Yeah, you're right.
Also, so in the previous word, are you saying that F lower star and G upper shriek? So in the notation PR L omega, I was wondering what that refers to here. So in particular, are you saying that F lower star and G upper shriek preserve colimits in compact objects?
Yes, that's what I'm saying. Yeah, on finer type schemes over the integers. Right, it's a bit, I mean, extending that to non-finite type things, it works, but it's a bit more subtle. Right, and somehow what makes this category, can make this category difficult to work with is the computation of morphism groups, namely the morphisms in this category. You get the twists right. Twist N and shift M, at least for regular X, they compute the rationalized higher Chow groups. Okay, and somehow writing down a morphism is equally hard as constructing something in here. In particular, if you're interested, sometimes you might want to know that such morphisms, that this group is zero, and then It's equivalent to that one being 0. Okay, there is part D. So there is an extension.
So the higher Char groups are known to be compatible with this, even for X, which is not smooth over a field or over a...
Yes, this is my understanding. I think this is due to Szynski-de-Vries, this extension. So, so far so good. We would like to apply this formalism in the setting of geometric Satake, where you encounter, for example, objects like the Hackestack. So you need somehow to say what is the theory on this more general objects, and there is ways to do this. And the way I chose is, so you look at the category of pre-stacks. So functors from rings to anima. Then actually I will from now on look at this Schrieg variant. So dm is defined to be dm upper Schrieg. This extends to functor from correspondences on this category of pre-stacks to presentable categories, also Lex monoidal. But let me make some space and say more. So it's constructed in a way that it's such a correspondence. So there's some restriction on the push-forward functor. Namely, I want this to be int finitely presented. Like this, and also let me list some properties that it satisfies. So, and then I also explain why I choose this version with the where you have upper Schrieg pullbacks for any maps as opposed to the upper star version. So somehow what is DMX on such a very general object? What you do is you approximate X in 2 steps by representables. Namely, if you spell it out, so there's a limit over all affine schemes mapping to X. So affine schemes naturally live in this category. And then there's a co-limit over all where A is a finitely generated Z algebra mapping to B. And then we have dm of spec A, which was already defined. Okay. This is what comes out if you spell it out, and I guess usually working with exactly this expression is not too helpful, but this is what it is. There's a couple of things you can prove about this. For example, like this, it satisfies étale descent, meaning whenever you have a map from the pre-stack to its étale schieffification, this will induce an equivalence. So,
sorry, Timo, could I just make sure I understand the definition? So this interior colimit here is a colimit along upper Schriek maps in the category PRL?
yes,
Okay.
that's correct. So all transition maps are upper Schriek maps.
Yeah.
Yeah, this is then why you naturally have upper Schriek for any map. And if you like, at that point, maybe it's just a notation. Yeah. And so, but here's the reason why to do this. Because what you would like to have if, say, you have an object which is a colimit with sufficiently nice transition maps, so with finitely presented and proper transition maps. Then can try to compute what it is, and first, basically by construction, this is the limit over the dm xi with upper Schriek as transition functors. And this you can, in fact, rewrite. So the reason is for these type of transition maps, the lower star is the left adjoint of the upper Schriek. And this you can then write as a colimit over the dm xi. Okay, where here you have lower star as transition functors. And I guess the reason for this is that if you have that presentable with right adjoints is also the supposed to presentable with left adjoints. So you can change the limit into a colimit, but this you can only do if you have here the left adjoints available. And then this is somehow a way to think about this is that your category here on this union is the union of the categories on the single strata. And the particular case is when all these transition maps are closed immersions, say, as will happen for the hacker stack, for example.
So the indexing category is what? Is a infinity or usual? Could the column with xi is over what indexing category?
Over what indexing category? It's well, it's any small category. You don't need it to be filtered, for example. You don't need it to be filtered, for example. It's any small index category.
Sorry, what do you mean by PR presented under right adjoints or left adjoints? I don't know.
It's an infinity category of presentable categories, and then here as functors you have the right functors that are right adjoint, and here in particular preserve limits. And this is somehow, if you think about this equality, it allows you to switch between the limit and the colimit.
And your pre-stacks are accessible or something like this? Do you take any functor from rings to anima?
Yes, I should say they are accessible. Yeah. I mean, one drawback, if you like, of this, but it's simply the way it is. You only have sometimes the left adjoints available of these functors. So in particular, it's not a full-fledged six-functor formalism. So the left adjoints you at least have for finitely presented maps between, and then there is not a really unique term for this in the literature, but the condition is usually referred to as placid. So, but one has to be careful. I mean, there are several meanings of this in the literature. And let me just say, for example, it's satisfied for the inclusion of strata in the hackestack. Okay. There's one more thing I would like to discuss about this before coming to the hackestack. Namely, it's on subcategories of Tate motifs. For doing the geometric Satake, what you have to be able to is to define a T structure on these categories where you have some control. And conjecturally, these categories admit T structures and are the derived category of an abelian category, but this is not known. But what you can do instead is to not work with the big category, but work with a smaller category, which is adapted to the geometry of the objects appearing in your example. So let's again do this for X finite type schema over the integers and look at the following definition. So we have, call it DTM of X for derived Tate motifs. And this is the full presentable subcategory generated by shifts and twists of the monoidal unit. So, and that, and inside here have a define the connective part, or serving as a connective part of a T structure, to be the category generated by. So you include all twists, but only only positive shifts. So for all n in Z, and here. I mean, if I put this lesser equal upper zero here, I'm using cohomological convention, which leads to looking at this for m greater equal 0 and generated by what? By colimits and extensions. So okay, so you can use this category to get a T structure. So the T structure on DTM of X. But of course, you need to know something in order to be able to control the heart of this T structure. And I guess it's the following lemma. So if we have the following vanishing, so namely you want basically negative X groups to vanish. So Qn twist M. This vanishes, so here let me refer to this as star for all n in Z and m smaller than 0, then the heart of this category here, this is generated by the compact objects Qx n for n. Okay, maybe let me also introduce a notation for this. This will be referred to as MTM, I guess, for mixed state motifs on X. Okay, what are situations where this vanishing here is known? So basically, I mean, there's some other cases, but basically, what you know is that this vanishing holds if X is, let's say, of the form spec A, for A being either a subring of Q bar, so this is due to Borel, this case, or A is a subring of the algebraic closure of a function field. This is due to Harder and Quillen for finite fields. So a particularly nice case is that of a finite field. So here you have an explicit description of this whole category, which is simply the derived category of derived vector spaces with a Z grading. So here in this case also you have no homomorphisms if m is 0 but n is not equal to 0. Okay. Yeah, and then the heart is just the category of Z graded vector spaces.
Excuse me.
Yes.
So in these examples, is this lemma known for also Misnevich topology or integral coefficients?
Yes, this also works in this case. Yeah. I mean, this you can find in, for example, this work of Kass, Vandenhofer, Schollbach. Okay, so let me now apply the setting to the Hecke stack. Namely, I would like to fix G's split reductive group over the integers. And here's following definition. So look at functors from rings to groups. Namely, look at the equal characteristic setting. So These are the raw serial valued points over R in your group G, and also sometimes referred to as the loop group. And in here we have the subgroup of, if you like, contractible loops or positive loop groups. These are power series valued points in there. So positive loop group. And the basic gadget for this motivic Satake equivalence is the Hecke stack. Oh. I see. Which is a double quotient from the left and the right. And maybe you étale chiefify it, though if you look at motives on this, the theory doesn't, motives on this doesn't see the étale chiefification. This is a nice pre-stack and call it the Hecke stack. And so, mention something about the geometry of this object. So, the Borel pair, so a split maximal torus and a Borel subgroup in G. Then this underlying set of the stack is simply the positive, the dominant co-characters. And the topology here, this corresponds to this set induced with a partial order, and one can show that's induced from the Bruyère order you have in this sort of things. And particular, you get for all dominant co-characters, we can look at the points of, so we get an induced point on the Hecke stack. And here we have, it's a stratum, and here's the closure of the stratum inside here. Oops. So this map here is finitely presented closed immersion, and this here is a finitely presented open immersion. Oh, how do I do this? Here's the following lemma, which makes this object well behaved. So let's look at one of those strata indexed by some mu. And this is also the same as the classifying space of, well, the group of automorphisms at this point. But this group has a nice shape, so where L plus mu. This is a semi-direct product of like this, and this here, this U mu. This is, well, it's basically a split unipotent group, except that well, it's a big to big, so it's an inverse limit of split unipotent groups. And this year, L mu is split reductive. So this is something you have to somehow prove by hand, that the stabilizers of this shape, and in particular has such a Levy decomposition. Okay. What this allows you to conclude is that the category of motifs on the stratum of the Hecke stack is particularly simple because of the A1 invariance. This split unipotent part goes away, and you're left with so the canonical map, I guess, in that direction, and this is due to the A1 invariance. So, for example, if you would work with a non-A1 invariant theory, you wouldn't have this easy description here. Okay, so should do it. Okay, let me do it like this. Since we have a somewhat solid formalism, there's a nice way of defining a monoidal structure on motifs on the Hecke stack. Namely, you have a convolution product on this, and it works as follows. So let's look at X to be the classifying space of L plus G, and going to the classifying space of LG. So this is a map with fibers, the affine Grassmannian. So in particular, it's int finitely presented proper. And this allows us to do the following. So first note that if you do the self-product of X with itself, this will be the Hecke stack. Namely, I mean, what is an object here? It's an L plus G torsor, another L plus G torsor, together with an identification over the puncture. And this is exactly what the Hecke stack is. But on the other hand, this is also the inner endomorphism in the following category of that object X. And here C is the category of correspondences on pre-stacks over Y. Okay. In particular, in this correspondence category, this has a natural algebra structure. And then you apply the fact that dm is Lax monoidal to see that dm of the Hecke stack is a monoidal infinity category. I mean, for example, the convolution is associative. And the advantage of doing it like this is really to have this category equipped with an algebra object structure in a homotopic way. But let me spell out what this means explicitly. Oops. So explicitly. So this is nice. So we are supposed to give an algebra structure on this object here, in particular a multiplication in this correspondence category. And this works with like multiplying matrices. namely you first so the outer ones you leave fixed, it's just identity, and the middle one you map diagonally into those two. And then this is the pullback operation, and then you do the push forward operation, and there somehow you integrate over the middle term, meaning you preserve the first and third projection. So projection 1, 3. And what does it mean in terms of the Hecke stack? Here is Hecke times Hecke. And what is this gadget up there? Well, it's 3 torsors with iterated modifications. And another way to write this, simply such a contracted product. And then if you project to the first and the last one, what this corresponds to under this identification is the multiplication. It's induced by the multiplication on the loop group. And yeah, and this is somehow the canonical projection you have. And then convolution of 2 sheaves. Well, it's rather computation than definition, is star push forward and then the Schwieg pullback of the box product. Okay, let me I mean, this you can write down directly once you have the formalism, but you don't a priori know. I mean, you want that is associative. Well, this you can also do in the diagram chase, but if you then want it in a homotopy coherent way, you have to say something more. So let me come to the last part, so stratified Tate motifs. Here's the definition. So I also write it DTM on the Hecke stack. It's the following subcategory, so it's a full subcategory of those motifs on the Hecke stack, such that the pullback to all points is state, so such that mu upper Schwieg of F this lies in DTM of spec Z for all mu.
So what is the unit for the convolution? Is there a unit?
Good question. There is a unit for the convolution, and in the language of correspondences, this unit is induced by a correspondence from X to the product, and this is a star push forward of the diagonal, and of what? Of somehow the upper Schwieg of the unit from the base. So
before you had this notation DTM only defined for finite type schemes over spec Z.
Right.
And now you're doing kind of an ad hoc definition for this specific.
It's an ad hoc definition. You can do it a bit more general, but basically in order to have this work well is you somehow need the geometry of that object to be Tate in some sense. Right. So so, and we have also the connective part. This is generated by the ones such that mu upper Schwieg of these lie in, well, in the connective part here, but there is some shift, and this shift depends on mu. It's the pairing of 2 row with mu. Okay, so with this you again get a T structure. Let me call this the perverse T structure on DTM of the Hecke-stack.
So where does the 2 Rho mu come from?
It comes from the dimension of the orbits inside the affine Grassmannian. This is where it comes from. Which somehow plays in the background in the way I formulated it here. And let me, so it's the joint result with Jakob Schollbach from 2019. And it's 1, so somehow, well, since we have restricted our attention to this very small subcategory inside all motives, there's some things you might want to check. So for example, this is stable under the operations iota mu, sub A, iota B, upper B. So for all AB, either star or shriek. So this exists by the general formalism of these placid pre-stacks. And for all mu dominant co-characters.
Did you do mu and mu prime?
Yes, you can do mu and mu prime. Oops. Let me also say there's also a good notion on the stack of Verdier duality, which I didn't explain, but it's also stable under this. And under convolution. Okay. And maybe let me make this a mu prime. So this is something you really have to use the geometry of this Hecke-stack in order to show this.
DTM less than 0. About bigger than 0, 1, you have this duality to define the co-connective part. And how to define the you have a T structure, you should have a.
Oh, I'm supposed to have a co-connective part. I mean, it's like the orthogonal to the connective part. Right. You can ask about, do I have a more explicit description of this co-connective part? And this is also true. Yeah. Yes.
So also, so somehow in the Tate condition, there's no restriction on how the reductive group acts.
You don't. Sorry, say again. You don't have a reductive group.
I mean, well, like there's no condition on how the reductive group acts. Like you just pull back. I mean, you could have pulled back to the point mod the group, but you actually just pull back to the point in test. If that is
right. This is exactly. If I wouldn't have a bit more time, I would have explained this. This is exactly where this condition on the stabilizers comes in. Namely, the stabilizers up to some pro-unipotent part which you ignore is a split reductive group again. In particular, it's connected, and it also has a cellular geometry, so the cohomology state. And this is where it comes in. But you're right, one has to be careful. I mean, this is really tailor-made to this Hecke-stack. Let me finish the statement here and then stop. So you have perverse Tate motives on the Hecke-stack, which is defined as the heart. And it's generated by the intersection complexes. So what are these in that setting? So you So let me write it and then write down what it is. Fixed star, so for all mu here, and L is a mixed state motive on spec Z. And F mu is the structure morphism of the Hecke stack. And also somehow this shift here is dictated by the dimension of the corresponding stratum in the affine Grassmannian. And third point, and then I finish, the convolution is T-exact. Particular, we end up with a monoidal category, and this will be the one where this motivic Satake equivalence is modeled on. I stop here. Thanks.
Are there any questions?
Can you say where did you use excision?
Sorry?
So where do you use excision in this?
Excision triangles, they're basically used all the time, but let me pick out one point where it's particularly important. Namely, if you would like to show that the convolution preserves this subcategory here, the key point to consider is you reduce the question to the affine flag variety, and then you convolve Schubert variety attached to a simple reflection with the Schubert variety attached to the same simple reflection. Okay, and if you spell explicitly out what it means, there is you get like an extension of two things which comes from a excision sequence, and yeah, this is for example one point where it's used.
So is it true that your categories that you consider big ones, and do they have compact object? I mean, they are in the compact part already?
Oh yes, this is great because it's one has to be really careful. I mean, like these pullbacks here. Well, the motives here is motives on the classifying space of a split reductive group. And these pullbacks, they are not compact objects in the derived category of Tate motives on the stratum. But after cutting it down to the heart, these objects here will in fact end up to be compact in the heart. These objects are compact in the heart, but they are not compact in the bigger derived category. This is some subtle point.
But if do you think that the full category is like the derived category of the art or not?
No, this I'm not saying.
This is just not true.
Yeah.
Even. Yeah.
Is there any concrete descriptions of Tate motifs over classifying stacks?
Well, you mean yes? I mean this. Well, I guess part of the subtlety is the category of Tate motifs on the classifying stack is compactly generated, but it's just that the compact generators are not like the Schwieg pullbacks from the base, but they are rather the star push forward from the universal cover by the point of things up, compact objects up there.
But is there a more concrete description, like in terms of, I don't know, Tate shifts on spec Z and some descent from that? What is it?
I wouldn't know. I mean, you can. The motives on this classifying stack, it's an inverse limit, right? And you can calculate the star push forward and in each term see what you have.
No, but like topologically, for example, if you have BG where G is connected, you could classify like in terms of co-modules or G's on BG or like.
Good question. I don't know. Yeah.
Are there any other questions? Okay, then let's thank Timo again.
Thanks.